Okay, welcome everybody to the second keynote of our conference. It's my pleasure to welcome Zhou. She is associate professor at the Computer Science Department of the Columbia University, working on real-time, multimodal, intelligent, interactive systems. And at the same time, she's co-founder of Articulate AI, working on democratizing AI agent building with Gen AI development tools. She received her PhD at CMU, working with Adam Black and Alex Ratnicki. She was listed in the Forbes 30 under 30 in 2018. The same year, she also, together with her team, won the Alexa social bot competition. She has more than 200 publications and received many best paper awards at recent top-tier conferences. So please join me in welcoming Zhou.
Thank you. I want to make sure that this talk is also very conversational. If you have questions, do raise your hand during the talk. Today, I'm going to talk about AI agents beyond ChatGPT. So I mostly work on conversational agents for many years. And because of the wave of LLM, I think for a lot of people in this room, it's very simple. The idea is how could we re-navigate our conversational systems under the wave of large language model? So we all know large language models like ChatGPTs have really diverse skills. And this is really coming down to become a sort of a general population. Everybody on the streets is talking about it can do compiler work, it can do interactive debugging, so like co-pilots. You can do marketing, content generations. So there are a very famous couple of different companies that are commercializing this. And there is a writing assistance. Nowadays, all of my undergrads who are taking my course are using ChatGPT to do some homework at some time. So we all know it can be repurposed for very different things. It's really coming down to because the natural language interface, the freedom of you can type in anything as an instruction, make this tool super popular for anybody on the streets who can write. So at the same time, we also do see there are a couple of different things that the ChatGPT or simple interface chatbots cannot do, which is perform actions, complete tasks. So this is very similar to what we always talked about in dialogue systems. For task-oriented systems, we wanted to make sure it completes tasks. It's useful. It's actually impacting the real world. For example, being able to book tickets, being able to serve as a travel assistant, and in industry settings, being able to complete automated flows. So simple casual chats has limited capabilities in terms of impacting everybody's life. Of course, having a best friend or having a sort of a counselor in some ways in a social settings are useful, but there are much more bigger space you can conquer if we can link language with actions. And also through the actions, we can complete certain tasks and perform certain goals. So there is definitely a lot of talk about AI agents. For me, well, for a traditional conversational agents or a dialogue system person, I really do see we have been changing different ways of layering out concepts. They're different in slightly different ways, but in general, a lot of the core functionalities are the same. When I say dialogue systems, like probably before the neural network stuff, we usually just call us dialogue systems, right? We build systems through conversations in order to complete tasks. Well, later on, because of the neural network, everything is calling themselves AI. So we wanted to fit in some AI in our topics, and then it becomes conversational AI. So some of my courses, my special topic class has been changing names from dialogue system into conversational AI. Recently, I have been changing it into AI agents. The idea is still similar in terms of the vein. It's like through conversations, humans and machines can collaboratively perform a task. Sometimes it doesn't involve actions, but most of the time it involves actions in order to complete a task, like book tickets, plan a trip. And sometimes in AI agents, we have a little bit more than simple completing tasks through conversations. we can actually enlarge it into not necessary language. It could be code. So code snippets to execute for APIs in order to construct automated flows. So that basically touched into the space RPA tools. So I would think AI agents is a little bit larger than the conversational AI space, but it has a lot of the core functionality the conversational AI people have been working on for decades. So Andrew Ng had an idea about how do we break down key functionalities or limitations that current AI agents are suffering. So first, we have been seeing a reflection of self-correction as a way large language models have been improving itself on. So reflection is simple as you can ask the language model, how are you doing? Are you making mistakes? And based on this kind of reflection of feedback, you give it back to the large language model and ask it to self-correct. So this particular functionality, originally when we say for reflection, it's sort of like a trick. But in itself, you can think about generation is hard. It has a much larger space to search for. But once that you already generated an answer, and you ask the models to say, is it correct or incorrect, and give them feedback, which is much less sort of space to search for. It gives you more certain answers. So this kind of sort of a reflection self-correction is actually very useful in terms of the trick in helping language models instead of retraining it. So we had this paper in NACL 2024, which is an outstanding paper. How do we teach large language models through self-improving? But not particularly only on large models, but we're trying to make smaller models to be able to learn the self-improving skills through interactive demonstrations for large models. And then later on, another important aspect is called tool use. When we say large language models, previously, a large language model is just in itself finding all the pre-stored information from the pre-training processes. But if we add on tool use, you make the large language model much more useful. What is tool use? It's really coming down to if the model was instructed to do certain things. You can actually, instead of using the internal knowledge of the model, but think about what are other possible tools these large models can call. For example, you can call a Python code that will be pre-written for math deductions. Or you can call like an API that gives you a place of interest to search if you're traveling. So these kind of tools can make the models, basically these models, much more useful. So tool use is one of the things people have been working on, including my work. So here, a lot of people are focusing on API callings. So recently there are new data sets like Gorilla from Berkeley, all very interesting things to look at. Another thing is whenever we added the tool use and a reflection, then these are basically actions, right? We're instructing the models to do reflection. Reflection is one type of action. And tool use, dispatching the tool, which tool to use. This is also another action. So if you are actually making the models to do one thing, right, he can choose different actions to perform. And if he gets some feedback from the reflection or self-correction, you can actually replan it. So planning is actually very critical. Planning is sort of an extra sort of capability we added to the models. Before, if we just prompt ChatGPT, very vanilla, you're just getting one chance to get it right. But now if you have a plan, you can select different actions to perform. And based on the feedback, these actions, after the performance of these models, you can correct and do other things. And then this process of iteration gives you better answers or complete tasks better. And of course, requesting more information from the users, which is like the traditional conversation, is another action that these models could perform to further refine the task processes and get to the goal that is more aligned to the human's intention and instruction. So planning is very important. We had a couple of papers in this area, for example, this is like sort of revamping of multi-college research. So it was pretty popular among the original RL works of like the famous goal from Google. But multi-college research is actually very effective. even in the planning within the large models area. So we also had another paper with Microsoft Research on if we don't change existing large language model, can we improve the factuality of these models through planning some of the actions performing. And again, once that you have one action, you will have one task that you completed. We wanted to make sure that different agents perform different tasks and how these agents can collaborate together. You don't want to build an agent that you say, I can do everything, because sometimes it's like waste of energy in terms of making it too general. You can actually coordinate different agents to make it more efficient. So this 4 elements are what Andrew Ng has been talking about. And I also very agree with every point, and we have been doing works on all of them. One of the things I wanted to add in is more on the pragmatics. So here we're mostly talking about execution, talking about semantics. But on other sides, there are pragmatics is also very important. For example, we had a recent work about, can we use conversational strategies like self-disclosure to impact the relationship between people and machines? Then to influence people in some way. For example, we do find if the chatbot actually do more intimate self-disclosure on certain tasks, like you're talking about movies or talking about hardships during mental health related issues, they are more likely to have better impacts to let users to accept their recommendations. So here, what we talk about is one step further. If we perform the right actions that is actually aligned with human beings, there are certain things from these kind of plannings. If you add the natural language generation with pragmatics, with user adaptations later, you can actually get better influence of the human. So it's not only aligned with the human instruction, but actually be better than human, or in some way collaborate in a different format. So this is a sort of a simple outline. I can't talk about every single papers in details. Particularly, we're going to go over 2 papers, the TriPass paper and then the LM augmenter. And in the end, I will talk a little bit about these days, how do we have smaller models to perform better than larger models so that you can have a very efficient way of performing tasks. So a little bit about background. There is a thing called in-context self-improvement. So you probably know in-context learning, which is the left side. You give the large language models like GPT a couple of examples that are similar to your test input. And then the models learn through few-shot learning. So on the right, there's what we call chain of thoughts. We are giving these models, what people usually call chain of thoughts, let's think step by step. So basically, then it will be able to sort of break it down and use these kind of extra steps to help it to get to the final answer. And then we combine these 2 methods together, which is the self-improved prompting. So instead of giving it just a few shots or give it a think by step, we're giving it examples that have step by step in the prompting process. And people find that it's very useful if you combine these 2 techniques together as a reflection. So this is one of the paper by previous people called self-refine. So what we find in terms of difference between large models and small models in this particular in-context self-improvement functionalities are pretty interesting. So we do find once so we did a very simple comparison. We compared like Codex and Llama 7B. So it's basically 175 billion model compared to a 7 billion model. So if you do this in-context self-improvement, large models can actually learn better. So you have like 2 point improvement and 4.4 improvement in various different hard tasks of logical and deduction. Well, if we perform the same measure to the 7B models, you actually have a degrade of performance. So although these large models can do this, why this method doesn't work for smaller models? And usually we know smaller models actually need more help in terms of these hard tasks. So one thing that we definitely see is if we look at how smaller models are leveraging these techniques, is we do find some of the intermediate steps have a lot of errors. So the intermediate process, like step 2, has an error. And this basically, this error basically propagates through the process. So this is, and sometimes you can think about the blind is actually leading the blind. So the process doesn't really help for smaller models because in itself, it's more error prone. So you have more errors and then you do these kind of loop, you get even worse. The simplest thing we were to think about is these kind of large language model, can they learn from demonstrations for large models? One of the big problems with these kind of large models, so here we use a symbol like the llama model, we're using the meta symbol, and the codex and larger models like our GPT, we're using the GPT-4 model. So you can see the steps are actually different. So if you use the feedback you got from the large models, you can't really teach the smaller models because it's irrelevant. So this is very simple to the idea is that you're teaching an adult a math problem, and you're using the feedbacks that from the adults of how they make mistakes, and now you're using these kind of feedbacks to teach kids, and the kids wouldn't even understand what the problems are. So you're basically miscalibrated in terms of the feedback and error. So you have to dumb the feedback down to the level to the smaller models to be able to let the smaller models to learn. So this is a very simple idea that we have seen for many different areas, is that we actually need to tailor the feedback to smaller models. And how do we do that? Is that we can learn from online demonstrations. So we actually reformulated the problem. We say self-improvement. Now, instead of thinking of it as a task, we think it as an ability. So we wanted to make sure that smaller models are able to learn the self-improvement capabilities. So in the future, it will be able to improve over itself. So, and specifically, we wanted to make sure that we accumulate enough of these kind of training samples for self-improvement. Specifically, we define self-improvement as a task. And then we can replay these interaction experience over time to actually help. And how do we have good interaction experience, sort of examples to help? So nowadays, we just look at the intermediate steps that these models have performed, and we use large language models to edit these models in some way, and these are teacher models, to modify these smaller models' attempts of trying to correct itself. So it's more about these models are making these errors. We're actually using the smaller, large models or Python scripts. Python scripts here in particular are, you can think about our tools that are specific to the task that has better results. For example, here, the Python scripts, when it comes to mathematical deductions, are like absolute values in terms of, you can think about plus or multiply and so on. So these Python scripts gives you ground truths of these simple arithmetics. So here you can think about, so for example, the smaller model makes mistakes 2 + 2 = 2. And then we have the teacher here, which is a large model, or sometimes a Python script saying there is a mistake. Maybe 2 + 2 should be equal to 4. Right? And then the smaller models would be able to take this into consideration and improve over itself. So the process is very simple again. So the training sample, and then we use smaller models to ask it to do the self-reflection. And then we use we identify errors here. So we use the prompt updates so we can actually update it itself here. So we use large language models to say your second step, the par 4 - 6 = -3 is incorrect. So this is because blah, blah, blah. And then you have this sort of the feedbacks to put it in as extra trace for your training. So because of this, right, so the original error trace is modified into the correct trace. And then we basically using this interactive trajectory editing to create a lot of data. And then we also reformat these data into attempt feedback and update triplets. So we have a lot of them over time formatted the same way. And we filter and rebalance these examples with different errors so that the model can learn more diverse and balanced data of these different mistakes and re-edits. So, and then basically we use a simple weighted SFT, and then with more emphasis on feedback and updated tokens. So basically a simple training policy. And then we conducted experiments to see how much we can improve these smaller models, like 7 billion llama models, on really challenging data set like Big Bench Hard. So here we see there are 4 tasks that we evaluated: multi-step harassment, word sorting, date updating, logical deduction. So all of them are very, all of them have diverse, different deduction, sort of different functionalities you can optimize to make sure that our method is general enough. So we perform 2 types of evaluation. First is, can these models, the TriPass model that with these kind of self-improvement training, can improve on the model's capability of self-improve? Can these models improve overall performance on the diverse 4 tasks that we talked about? We do see in all of these tasks, we're able to do much better, a little 2-point or a little bit better. This is 4-point, this is 3-point in general to improve after we do a couple of different iterations. So the reason that we do 3 iterations is because when you're doing editing, there's multiple editings you can do. So you can iteratively do it better. But here we only do it 3 times because we noticed that if you do more than 3 times, the improvement doesn't give you much. So there are certain certain plateaus you can do, and this plateau usually comes from these large language models or the Python scripts. They have upper limits as well. So in general, we can see for multi-step arithmetic, we can do 7-point for improvement. Word sorting, a little bit more than 7 points. Same thing with data understanding and logical deduction, we have much more improvement. So usually if it's a harder task, you get a little bit more improvement. And if it's really hard, you get even more because there's more space for you to improve overall. Okay. So we also did a couple of different ablation studies. We do see adding different trajectories, adding data filterings, adding different, so weighted SFT instead of simple FST, you all get some certain improvement over time. But the biggest one is still the interactive trajectory editing that gives you the majority of the improvement. Some of the interesting findings we see is the more iterations that you do the tripods, of course, your error rates are getting down. But they do plateau when you do after more than 3 iterations, because there are upper limits. But at the same time, sometimes we really do see LLMs themselves can detect these, sometimes cannot reliably detect mistakes. Because sometimes you can do it right, but you don't understand these models that understand these kind of tasks that very well. In general, we see these kind of limitations in terms of the sort of extra steps that you see. But over time, there are more things we can explore in terms of how do we leverage different promptings to help in the process of further reduction. So in general, this is just a simple way that we see how do we use smaller large language model that previously cannot do self-improvement to improve itself because of its error-prone propagation thing. But later on, we can actually make it better through this, what we call prompt editing. The editing of the trajectory really coming down to, if we wanted to teach these smaller models, we have to dumb down the feedback towards the level they understand. And the intermediate feedback has to be accurate enough to be able to make these smaller models to learn. So you can actually leverage large language models or sometimes scripts to help in this process. In general, these kind of on-policy of edit histories could be very valuable source of knowledge. You can use it to enhance different possibilities of ability of these kind of smaller models. So we're going to talk a little bit about later on in the end of the talk, how smaller models can even be better through these kind of on-policy, off-policy learning. Okay, any questions before I move on to another task? So the second paper I wanted to mention is how do we leverage a policy? So the previous one is about reflection, self-correction. It's a one particular action. So when we actually have different possible actions to perform, like calling a tool, calling an evaluation tool, or calling a reward, how can we actually improve these models' overall performance on things like accuracies in terms of factual information generation? So this idea is very simple. We have these large language model, and we have these users. One is on the other side. So large language models have some impressive intrinsic qualities, which means that no matter who uses, I need these abilities. For example, I need to generate human-like text. I need to incorporate general knowledge. I need to utilize retrieved knowledge provided by various search engines, for example, Bing. Right? These are knowledge every large language model should have, no matter who is using it. So these are what we call intrinsic qualities. Well, for users, right, they're motivated by extrinsic goals. For example, I want task one person, I wanted to write documents like emails. Task two, I want to get smarter, for example, be able to study physics very well. I want to get entertained. So for each individual task, you would have different attributes you want the large language model's generation to have. For example, for emails, if I'm writing to my professor, I wanted the style to be scholarly. For the second task, for example, I wanted to learn physics, but I wanted detailed explanation. So the style, instead of scholarly, I wanted verbosity. So really coming down to the user's extrinsic goals might not align in terms of individual attributes the model's sort of generation would look like. So how can we actually make sure that we just make sure that the large language model's intrinsic qualities are solid, and that they can adapt to individual extrinsic goals or attributes these users want? So this particularly is really coming down to wanting the model to just train really solid on the intrinsic qualities, and doing the usage will do the adaptations to individual users' extrinsic goals. Okay. So one of the main benefits of these reinforcement learning-based frameworks, it's really about adjusting language models for better groundings with specific goals, such as knowledge or either common knowledge shared. So you don't have to do large language fine-tuning, which is very costly. You can use reinforcement learning to guide the models to actually perform. So basically, this process of using LL policy is really coming down to you don't have to fine-tune. You can use any of this, so that you can use any of the large language model, whether this is open source models like Llama, or it is closed source model like GPT-4 or Cloud. So black box models could also benefit from these processes of large reinforcement learning in order to improve the final goal of the task. So the main modules of these reinforcement learning framework is still the simple ways that we define reinforcement learning. First, we have to have a utility. Want to evaluate extrinsic qualities reflective of user preference. So basically, the utility is really you have to align it with the user's goal. So the user wants to do A, B, C instead of like I think you should do this and that. It's really coming down to whether the user's quality user's extrinsic quality aligns with your utility. And then knowledge consolidation is one type of actions we could take. So for example, we retrieve from external knowledge. You can think about other actions you can perform as well. You can do like a call, like a mathematics solvers. You can call like APIs for weather, for locations, and so on. So these is one of these kind of modules you can do. But particularly when we're looking at factual generations, we're focusing on knowledge consolidator. And then we have the policy, which is what we call trainable modules that we can to control what actions should we take given the utilities that we align to. So this is actually combined, deployed with bin search. So some of the bin searches are using our policies to improve its final performance. So here is one example. For example, we have this particular question, which is what we call multi-hop questions. Which 2013 Los Angeles Galaxy player transferred in for a team with 12 international titles? So it's very complex. So what do is you go down to the Wikipedia and figure out what you can do. So first, so we have this player called Juninho, and it's transferred from a team called Sao Paulo. And then Juninho is, you can locate this in the running text. He's like played for Sao Paulo. And Sao Paulo, in addition to their 12 international success, it is a Brazilian club with the most international titles, right? And then, so basically based on the information, the ChatGPT thinks Jamie Fernando is transferring CSD municipal a team with 12 international titles. So this is actually an answer that we got from simply concatenating this particular instructions from the user to with this external knowledge, we basically make it everything the structured information into a string. And this is basically the answer. And then we asked the models to do the feedback, as simple as we said it before, right? Is it correct? So basically you can concatenate the two together and say, is the answer correct or not? And say the feedback here get from ChatGPT is play a Juninho. Jamie Fernando is transferred in from CSD Municipal, but there is no information about the number of international titles of this team. So actually, which is very exciting, the model is actually notice its own error from this particular like a self-reflection process. And then we basically have combined these kind of self-reflection with extra external knowledge. So basically we reshuffled the information based on the information that we given. And then all these three sentences from the top are concatenated together, plus the external knowledge to refeed it to ChatGPT. And we find, so the final answer is Juninho is transferred from Sao Paulo team with 12 international titles, which is actually the correct answer. And then finally, we feed it to the user. So how do we actually able to complete this kind of example is really coming down to the extra training that we have done through the LM augmenter architecture. So we have the environment, which is the human. Basically, he asks the question and expects to have a correct answer. And then we have the LM augmenter, which is our entire framework. And then we can use any of the large language model, for example, ChatGPT. And then you can consider the whole thing as an AI agent because it's performing actions, for example, reflection and create external knowledge again to get information that is more refined. So what it does, so there are a couple of things that it can do. First, for the large language model, you could, this particular box, you say, there are a couple of things you can do. Either you can execute a certain action, for example, you can use a knowledge consolidator. So the knowledge consolidator action basically calls external knowledge one more time with the extra information you got from the prompt. And the other one is like you use the prompt engine, which is combine everything you had before so far and then get the results. And then we know like these kind of all extra informations from the first feedback, first answer to the feedback and everything is all stored in the working memory. The policy is really coming down to, based on the working model, what kind of action should I execute? And based on the utilities, what are the things I should consider in terms of which actions should I perform? So here, the utility score of feedback is basically whether the question was answered correctly or not. If we have this particular factual answer, question answer task. If you have other tasks, for example, writing a email to a professor, then your utility is like scholarship and other things. So here is really coming down to very similar to the tripod. We want to make sure that the traces are stored in the working memory, and then the policy are learning through these working memory to be able to select the right actions. So for factual knowledge answering, it's really coming down to when should I ask for feedback to see whether this is correct or not, or whether I should call the knowledge consolidator to get extra information based on my feedback. Or at this moment, this is good enough. I don't need to do further actions. I can just give it back as an answer to the user. So this process, we were trained from a lot of these kind of experience that we played through actual being user searching and asking these questions. And then through the processes, we don't have to retrain or fine tune these large language model, but we can use the feedback. We can use additional knowledge consolidator actions to further improve the factualness. So the training process is very simple. You have human system dialogue model. Again, as a Markov decision process, you have a set of dialogue states. We're encoding them into working memory. So you can think about this is very similar to all these dialogue systems we have been talking about earlier. You have the history, you have the user query, you have the answer from the model, and you have a set of actions you can call. So these are actions that you can do. So the prompt engine, which is query the LLM to get answer. You can call the knowledge consolidator, basically query the external knowledge one more time, given all the previous information so far. And then you're actually trying to learn this transition probably, going from the previous states, using this particular action, going to the next. And then we have the reward function, which is extrinsic reward for taking action A in state S. So the extrinsic reward can be different for different tasks, but here we have it a model very explicitly for knowledge-based question answering. The extrinsic reward is whether this is a factual answer, is correct or incorrect. So basically, learning the policy to be able to move current state, which is the response, like including the response, to be able to having the correct answer, which is satisfying the extrinsic reward. And finally, we're basically learning a neural model by optimizing using a reinforce. So we tested this algorithm on various different data sets. Here is one interesting customer service-based dialogue task that we worked on. So we not only worked on the factual answering, but we also worked on other tasks. For example, we have the red line as a random policy. Random policy is because, for example, we have 2 or 3 actions, right? It could be more. You just randomly select an action at a time. While the blue line is that you actually learning using the policy that you learned. Given the action, you are picking the action that actually help long-term in terms of optimizing for the reward. And then ChatGPT is basically the baseline. So you don't do any of the action. You just you don't query. You just query the knowledge consolidator one time, and then you don't do, and then you do feedback, and then you get the answer. So you don't have the optimization process. So it's pretty stable. And if you do random policy, you do a little bit better because you did some actions. But if you do optimized one, you can do much better. And there is a huge difference in these tasks, for example, in customer service. And then we also did other things. For example, this is customer service. We also modeled a little bit on the human evaluation because it's a chatbots, right? Wanted to make sure that considering this is a human actually going to use this model, do people think it's useful, or do they think it's very human-like? So these are some of the metrics we also evaluated from the human side. So we do find that at least like a 10-point or 5-point of improvement. So I also did other things like your new chats and other data sets in terms of validating this algorithm's generalizability as well. So we all do find whether we use different search algorithm like BM25 or use golden answers, the improvement is all very universal. But in general, when we talk about knowledge consolidator, there's also a sort of trick in terms of how do you do knowledge consolidator? Because we know there are structured information like tables, and there are semi-structured information. For example, these kind of like your annotated ones that you can go through linkers, and there is a super unstructured one. So a lot of times when it comes to factorial question answerings, it's also the accuracy of these models heavily relied on in terms of how well your knowledge consolidator do. So this is coming back again. So for this entire processes of AI agents, every individual steps has to be good. For example, you have to have a self-reflection ability that is great. You have to have a reliable tool calling ones, and your tools have to perform really well. So knowledge consolidator is one of the actions. You want to make sure you reduce all these errors in terms of action process errors. And also the planning is like one step even further. You want to make sure that the reflection, which is a lot of times considered as reward, and also your actions are performed well instead of having all these kind of errors to propagate through your learning processes. Okay. So a little bit of the closing. I really do see the large models like ChatGPT or GPT-4 or the new ones, GPT-101, they're really great in some sense. But when it comes to expert tasks, like for example, I wanted to be a really entertaining comedian. It can't really be. So one of my students are working on how to generate humor. So they can do some things, but you can't really do the level of the Hollywood comedians. And then when it comes to healthcare, then it's even a lot of more things that we wanted to design for these current models. And in education as well. So Khan Academy has to deploy some of these kind of education systems, but they're far from actually useful in helping students to learn better. When I really do think that these kind of sort of ChatGPT or GPT-4 are, people say like jacks of all trades. They can do something, but they're not expert in anything. So how do we make these kind of accountable with these models accountable with domain knowledge? How do we distill these domain knowledge, or either law or healthcare, all these informations into these models will be really interesting. One of the things that we also did over the years is really coming down to how to make smaller models do things better than large models. And this is really coming down to we're in academia. We don't have a lot of machines to train really large models. But there are a way we can use smart learning processes or machine learning algorithms to still make the smaller models to be useful. Because the entire idea of machine learning is really coming down to use good algorithms to make a model more efficient. So smaller model is always good and it's always going to be useful. It's simple. When I talk about it, it's really coming down to, if you ask Amazon, what are the 3 advantages you have? We say faster, cheaper, and more reliable. So for a machine learning model, it's the same. You want a faster model, cheaper model, and more reliable model. And for a smaller model, you can usually be faster than bigger models. And cheaper, of course, because smaller models has smaller capacities, smaller parameters. You require less of the memories to run. And of course, it's also good for the environment. In general, how do we do these work within the realms of learning processes? So one of the things that we've done is called Lion series. So we took these smaller models like Llama 3, like 2 billion model, 7 billion model. I wanted to see, can we do basically alignment learning, or sometimes people call it instructional learning, to actually improve these models. So we actually did a sort of a more open source processes. There are a lot of different papers talking about mixed match or different like pre-trainings and data processing issues to train models. So usually you start from SFT, supervised fine-tuning. So you have various open source SFT data sets. So here we evaluate different ones and combine them together to do a more holistic one. And then you do what we call offline DPO. Offline DPO, DPO is one of the reinforcement RLHF, reinforcement learning with human feedback type of algorithm. So open source DPO data sets are everywhere. but some of them are good. Some of them have a lot of noise. Some will have a lot of overlaps. And then later on, you wanted to do online DPOs, which is what we just talked about earlier as well. Online learning usually is always better than offline learning because online learning traces are more tailored towards your current model's capability. So through iterations, your models can do better. So these processes are usually, we test them multiple times. It's the best ordering of how to improve your model over time. You start with supervised fine-tuning because it's the basic thing that the teacher then needed to distill the information to you. And these open source models, SFT data sets are pretty good. So you can think about all these kind of shared GPT data sets. And then the offline DPO is really coming down to the comparison data sets. Because once you learn from like a reading text, you wanted to learn comparisons. Because comparison teach you more things than simply learning from copying data, right? Predicting next word. So the comparison is A better than B, which is what the DPO models are doing, right? And later on, as you wanted to adapt to the current model's ability to do online DPO. So we can actually do much better than simple models. So we train on like a Gemma 2B models, for example. We start with Zephyr model, which is very popular. Which is a SFT plus DPO model. And then later on, we redefine all the processes and redefine a lot of filtering of the data. We can do much better to 55 compared to the original 46 model. And then later on, we also did similar things with Llama 3 8 billion. So going from 71 to original 68. And then a lot of times, we can actually make the 2 billion model as good as the 7 or 8 billion models if we do the right processes. We have this everything open sourced from how do we prepare data, how do we combine data into different processes in different stages so that you can reproduce this through downloading or Hugging Face models and GitHub. So we have a lot of exposures over the years. Over the past couple months that we just released this paper. This is the paper on the submission of EM&LP. I really do encourage all the communities to be able to do reproducible work because most of the time when we look at these companies like OpenAI or Anthropic, they're not telling you what data they're training on, even or releasing their model parameters. Even for Meta, they're giving you the parameters, but not telling you what data they are trained. What are the detailed training processes they have been doing? So being able to reproduce things that are more compact is going to be very useful for a lot of people who do not have the resource to do models that are super large. Again, for other things, we do see there are more and more these kind of RAG frameworks. So retrieval, augmented generation. So RAG frameworks is pretty pervasive when it comes to chatbots. So people are retrieving information and then combining it into generations. But we also had a paper, I think really interesting, is about how can we make this kind of RAG-based pipelines trainable? For example, this is all open source. You can also teaches you from how do you prepare data, how do you train your retriever, how do you train your generator, and how do you assemble these models into a reliable pipeline? And also, how do you evaluate these models? And how do you iteratively deploy and improve these models through interactive UIs? So this is the way that we help the researchers or ML engineers to be able to do it all by yourself. Everything is open source. So you don't have to rely on GPT-Ada for embedding or GPT-4 for a generator. So you can actually get a more fine-tuned version that is more tailored towards your domain. Couple of other things I really think the ChatGPT or GPT-4 are still lacking is about adaptations to different users. For example, I've been working on this problem called persuasion for a long time. We wanted to see how systems can persuade people to do things. So for example, when people say, can you persuade me to do more exercise? You just get very passive. You think out of your long things, benefits to regular exercise includes A, B, C, D. You should do this and you should do that. But in general, it's very passive. It's very generic answer. But in reality, what people usually get when you actually talk to a professional, nurse in like these kind of different programs to help you on weight loss or keeping you fit. Usually you have to do what we call, we start with the user saying, what's holding you back from exercise? The nurse was saying, my workout, the nurse is from the left. So what's holding you back from exercise? And one user may say, my workout buddy moved away. So you start with eliciting information from users instead of just giving them generic answers. And then you wanted to tailor to the feedback towards the individual user. So here particularly is like social support is critical. Maybe you can join a running club, right? You have to incorporate your domain knowledge from this. So for example, you can do RAG-based systems, or and more intrinsically, you have to have this kind of RAG more specifically trained on your domain data in order to be able to do this. So one thing, like again, this is what I usually call like, people want you to do certain things, like giving you an instruction, persuading me to do more exercise. You can't just have one answer to complete the task, because this is definitely not completing the task. So what it should do is be able to really do this as an AI agent to think about how to sort of compose these tasks into different steps. For example, starting with asking what's the reason of holding you back from exercising? And then based on the user's input, right? This is one action, you get some feedback from the user. So you can use this as additional information to complete your task. And then you also need to be able to respond to the user to be able to and ask more suggestions. For example, maybe you can join a running club. And then maybe this user says, too busy with my work. Right? Again, the passive answer, you have to analyze what's going on, and then saying not having time for yourself is tough. So this now goes on to more mental health related domains. Like you have to acknowledge the difficulty of completing the task. So this goes a little bit more deeper into the domain knowledge. And then pragmatics as well, how to express empathy. And then finally, let's try to make exercise a routine, and then suggest an alternative and start some actions. So being able to complete a very complex task, like persuade you to do more exercise, requires a lot of actions throughout the process, from decomposing the task into different actions based on the user's reaction, being able to replan the processes, and then finally complete the task also requires a lot of about mental health related issues or what we call pragmatics in order to perform these tasks. So finally, there are various other domains that requires a lot of these kind of systems, AI agents, to be helpful. For example, in e-commerce shopping experts, there are more and more people looking into like shopping companions. Right? When it comes to this, it's also about if you want to influence people to do purchase, right? This is behavior change. Behavior change is really difficult, which means that you're not only performing actions, you're changing people's mind. So that requires a lot more, just decomposing the task and executing semantics. It requires a lot more in terms of understanding, in terms of human psychologies, and also the persuasive pragmatics. So finally, one thing I just don't want to leave without ending my talk is about user privacy protection. So we all now know something is like, for example, my students, when they're actually generating their resumes, they're given everything they have, like their name, their location, address to the ChatGPT to generate these. And this potentially has huge risk in terms of protecting, in terms of getting bad actors. For example, let's take a very simple one. Say, hi, Tom, did you finish your workout today? It's the same scenario, right? And say, yeah, I went to 24-hour fitness as usual. And then you have all these kind of traces that GPT-4 collected about yourself, and they're going to use this as the training data to train their model. And then a hacker could come in and say, do you recall where Tom usually goes on Monday? Right? So goes to 24-hour fitness. So maybe he can go into your house during that time to do some bad things, right? These informations have a huge risk stored in your large models and can be recovered from hackers. So this is a lot of things like when we talk about differential privacies or these kind of federal learnings are addressing. So I just wanted to bring it up again. For example, my students Wei Yan has been following up, working even further on this directions. How do we protect user privacy when during the large language model world? How do we make sure that certain parts of your information, like your personal information, credentials, don't go into large language models? So finally, I would like to thank everyone and take some questions.
Thank you very much for this very inspiring talk, and please ask questions.
Thanks a lot for your talk. So you brought up privacy as one issue, but pervasive, but technology certainly also have other issues, right? With respect to, especially as they would get, to know more about psychology, more about individual users. They could be manipulative. They could be used for very bad purposes, right? To sway, private opinions and overall,
Yeah, influence political elections and stuff like that.
exactly.
Yeah, so this definitely has been always a problem. And large language models have been more sort of making this potential things more accessible for everyone. But usually in general, I would say like it's really coming down to how do we regulate the usage of these models. We definitely do see that, for example, the ones that we have been working on is more about this task has like a human actually wanted to do this. For example, a human has to say, I wanted to do more exercise to help my body in order to get into the study. So it's more about making sure that they are aligned with the study in the first place. But of course, in reality, not a lot of people are doing this. So this also comes into this like scamming process, right? So there are a lot of people got scammed by a large language model pretending to be certain people and persuade them to wire the money in some sense. But on the other hand, we looked into other things. For example, can actually these AI agents being able to defend humans on top of that. So we had a paper a couple of years back as how do we make agents, like for example, if bad actors cause your phone, to actually screen them out so that you don't have to get sort of under the risk of being scammed in some way. So it's really coming down to how do you utilize these technologies, but at the same time, these technologies are already out there. So everybody can use GPT-4, everybody can prompt GPT-4 to do certain things. And then depending how you do things like you jailbreak it. So at the same time, I think like we have to be more careful about this and educate the public certain things. Or for example, what are the sort of general ways that you can detect these are actually from the AI. But at the same time, we wanted to make sure that whenever you do like these kind of open source models, you have these kind of disclaimer that couldn't be used for certain purposes as well.
Thank you. A lot of great work. But you started off saying that you were moving to agents and the models doing action, but I think all the examples you showed were it was speech action. So there's task oriented, but there's always a human involved receiving the information. As the previous question is about, there were issues there of influence or how people take it, but it's potentially even more dangerous if you let them do actions in the world, if you let them buy the thing for you as opposed to advising you what to shop and how it drains your bank account. And then things like the Microsoft update that crippled the airline. So that was without LLMs, but if we really put this as agents in the world with the ability to act in ways other than just providing humans with information, what do you see as the?
Yeah, I totally agree because nowadays a lot of companies are talking about these autonomous agents, but none of them are really deployed them because of these kind of security risks. So one of the things that people talked about is really about security levels. You need security levels to be able to call certain APIs. So if some of the APIs is high risk, you need human approval to be able to perform the action. And you need a different level of human authority in order to be able to perform these actions. I think that will be definitely some of the things will be built in as the planning as well. For example, this is a low risk task. You can do it multiple times, doesn't matter. But if it's a high risk action, if you want to do it, you need a certain cost for it.
But
So
who determines that? I guess.
yes,
It could be, if you're spending like, $1 on a cup of coffee, that might not matter, but if you do it a million times, that's problematic. Or, Microsoft does it, it's nothing, but if somebody that's, just on the poverty line does it,
yeah, that's a huge problem for a lot of these kind of agents. If you deploy it, basically it's doing things on your behalf, right? So it has to learn like certain regulations in terms of this person cares about this, doesn't care about this, and certain things are really critical to it. I think like first it's like you have to have the human to define some of these critical things, and later on it can learn from the experience of this human approved this, but did not approve that. And then you can learn from these kind of like rewards overall as well.
That's one.
Thank you very much for very nice talk. So I think your talk have many indications, but yeah, as you show some examples, probably the language model itself may have some problem like privacy or cannot adapt to the user. But yeah, as indicated in your talk, so I think the language model can be controlled by the outside planner or something else, and I think what kind of information given to the language model is very closely related to some common grounds that we are doing. So do you have any kinds of what kind of information the planner should build for yeah.
Yeah, that's a really good question. So they're usually sometimes like we define these kind of states, right? You can have different information that is critical towards the task to be included in the states. So you have the context within in order to be able to execute. So this is related with respect to different tasks. You can refine it differently. Nowadays, like when it comes to agent, we're really coming down to say that maybe with the large language model's logical inference, it can be able to use the inference to be able to, for example, you're on a Windows laptop or you're on a Mac laptop, they can automatically detect these systems, and then based on that to be able to change in terms of what actions they need to do automatically. Instead of like, oh, I have to define I'm on a Windows laptop, I'm using Microsoft PowerPoint for slides or whatever, different versions, and then you need to do different things in order to be able to update models and those things. So I think that's one of the advantage of AI agents these days, because of the large language model, we think like there are common sense knowledge. They're already distilled in these models. It can do the logical inference to be able to fill these kind of gaps with respect to the environment they are, instead of you have to have a human to expertly define everything like the RPA tools that we've been using.
Yeah, thank you.
Okay, one final question.
Thanks for the great talk. When you're discussing about the self-reflection and the improvement, you are using Python script in the training time. My question is like, how do you have any opinion on using the Python script rather than in the training time during the inference time? How do you compare with using it in a training time? Like on the other side, you can use function calling and rather than training the model itself, like we are during the inference time.
Yeah, this is a really good question. So basically, instead of saying like we don't do any actions, we just do reflection, right? This is sort of the prerequisites of the task that we're performing. But instead, we can actually let another action become called Python scripts, right? But then the entire planning will be trained a little bit differently, because it's going to basically learn when to call Python script, right? So then the entire problem will be formulated slightly different. So the training traces will be different as well, but you can definitely formulate that way and then retrain it. So maybe it will give you even better results because your Python scripts will always give you the ground truth. Well, because we don't have this particular process. So that's why even with these kind of editings from the large models, these smaller models can still make these kind of heuristic errors.
All right, so we are out of time now. If you have more questions, we have lunch break now afterwards, so you can ask your question there. Zhou, I really like to thank you again for doing this keynote today, and we have this small present for you.
Thank you. Thanks.
You're very welcome.